Alright, so today I'm going to be explaining another important paper with the title Generating Graphs via Spectral Diffusion. This ICLR paper in 2025. So we present GGST, a novel graph generative model based on the spectral decomposition of the graph Laplacian matrix, a diffusion process. So we propose to use a denoising model to sample eigenvectors and eigenvalues from which we can construct the graph Laplacian and adjacency matrix. Using the Laplacian spectrum allows us to naturally capture the structural characteristics of the graph. This is very good for graph topology, and work directly in the node space while avoiding the quadratic complexity bottleneck that limits the applicability of other diffusion-based methods. Thus, in turn, is accomplished by truncating the spectrum, which, as we show in our experiments, results in a faster yet accurate generative process, and by designing a novel transformer-based architecture linear in the number of nodes. Our permutation invariant model can also handle node features by concatenating them to the eigenvectors of each node. So we introduced GGST. We define a forward noising process, always in diffusion, most of the time using this normal distribution, and we get the reverse distribution, reverse diffusion process. We call this denoising model. So we need to learn this and this, and it was originally worked on images, but then the people use it for graphs as well. But this paper is very interesting because it works directly in the eigenvector space. Instead of adjacency, instead of updating the STE for dx and the A adjacency and the features, they don't do this. They work on the STE, the dynamics on the eigenvectors. So let's call it d lambda. So you see the pipeline. During spectral diffusion process, you see on the left, the neural network is trained to predict the denoising steps for the eigenvectors and eigenvalue lambda of the graph Laplacian. In the second stage, it means that here, the second stage is graph predictor, where we train a provably powerful graph network. So once you eigenvalues and eigenvectors, given the eigenvalues and eigenvectors generated, it predicts the adjacency matrix. So we call it loss of adjacency. And here you have reconstruction. So always our adjacency is A, but so from A, because we have the diagonal of that, so we get the Laplacian. And once you get the Laplacian, it's very easy to decompose it like this eigen decomposition. So the score model takes the input, the noisy eigenvector matrix and eigenvalues at time t, and predicts the noise of the data to be used in the denoising step. The k-node feature eigenvectors are projected through an MLP to a d-dimensional space. The sequence of k eigenvalues is given as input to the 1D convolutional layer, which outputs d features for each eigenvalue. Both eigenvectors and eigenvalues go through a series of L layers composed of two multi-head cross-attention blocks. one updating the eigenvectors conditioned by the eigenvalues, and one updating the eigenvalues conditioned on eigenvectors. Interesting. After each layer, we apply a residual block, which adds to the layer input the updated values scaled and shifted by time-dependent factors. If the way brain works is so different from this AI that we are working, it's so different from that sometimes I think we never understand how brain works, because our paradigms is completely different from the paradigm of the brain. Brain is a spatio-temporal graph neural network, and I mean not the graph neural network that we know, so it's very different. So these methods, like this spectral diffusion and diffusion paradigm in general in generative models, are very naive. But we don't have any good paradigm better than Schrödinger bridge and diffusion and flow matching and these things, and some other variants of variational autoencoders. And we don't have any good paradigm because we didn't start to think differently. So the adversarial loss in this paper, the adversarial loss is the loss that you're familiar with. And we also have reconstruction loss. This reconstruction loss encourages the adjacency matrix predicted from the, first of all, diffusion models, diffusion-based graph generation methods. 90% of the papers fix the adjacency matrix. They know that, the scaffolding is fixed. And the next 10% that are based on like fragment-based ideas and those things are done by pharmaceutical companies because they care about pathway synthesizability, pathway, because in the pathway of creation of the graph, it should be valid. The reactants combine, so it's like a Markov process over trees. It's a sequence of trees. So that is more interesting for me than these paradigms that you fix the adjacency. Once you fix the adjacency, it's very limited. The model is very limited. So they did comparison on graph RNN, spectra, and for different measures like degree, clustering, spectral, orbit. And this is the comparison of eigenvectors. These eigenvectors, eigenvalues, it's very important. In positional encoding of graph neural networks, they are useful in capturing the structure and topology of any graph, or fundamental in spectral graph theory. So that was the motivation of this paper, and the rest of them is detailed. And have a good day.